Hello, in this video we will discuss the work done by a constant force on a system. So a lot of the words we used before, position, displacement, acceleration, force, they have meanings that resonate to their everyday lives. But the concept of work is very specific in physics. And to understand better what we mean by work, let me show you a picture. Imagine these three scenarios, A, B, and C, in which we apply a force to this eraser on top of this plank. As we can see, let's consider that the force is the same. Obviously, by observing figure C, we can see how the force will have no effect, nearly no effect, in the displacement of the eraser. However, and then we can see, or also depending on the force, of course, but let's say it's big enough, we can imagine that the eraser will move to the right when we apply the force at an angle. Also notice that we can also imagine that in scenario B, the eraser will move even more than in scenario A, because there is a component of the force which is parallel that is larger in this case than in that case. So now imagine that the force is 100 newtons here, but only 50 newtons here, or 100 newtons here and 50 newtons here, right? Or just consider the same scenario B. The motion of the eraser will not be the same if I apply 100 newtons or if I apply 1,000 newtons to the eraser. The displacement will not be the same. So all of this needs to be considered. The magnitude of the force we're using and also the direction of the force will play a role in how the eraser, which let's call this the system, let's say the eraser is the system, so the external force, well, comes from the environment. That external force crosses the boundary and modifies my system. With these ideas in mind, we are in a better position to understand what physicists mean when they speak about work. If you have an object, let's say the eraser, and a force, which in here it was pushing, here is pulling, it doesn't matter. We define work as, and I'm going to write the mathematical expression first. As the force applied on an object times the displacement that force produces times the cosine of the angle. In words, we can express it like this. The work done on a system by an agent exerting a constant force on the system is the product of the magnitude F of the force, the magnitude delta R of the displacement of the point of application of the force, and cosine of theta, where theta is the angle between the force and displacement vectors. So, what is going on? First of all, notice that force that we have here, let me put some green or something, can be decomposed in two components. This will be F cosine of theta, and this will be F sine of theta. Notice that the component of the force responsible for the displacement along delta R is F cosine of theta. The other component, F sine of theta, did nothing. How do we know? Well, because the block moved to the right. The block did not move up. So the F cosine of theta was the only component responsible for doing work. So the work is then the force that is parallel, yes, to the displacement, which in this case is F cosine of theta, delta R. This is another way in which you can express work. So a few things. First of all, notice that I did not put vectors up here. Well, not yet. Well, actually, let's put the vectors, but I am not going to put a vector on work because work is defined as a scalar magnitude, a scalar quantity with only magnitude. Another important aspect of work, it comes from the definition. The work done on a system by an agent. Just like before when we spoke about forces and we knew that there was an object and an agent. Now here, when we speak about work, it's very important to define what is doing work on what. An agent does work on a system. That's one way to look at it. Another way to express the same is to say work is done by, and here is the environment, on the system. Okay, so we define the system, we define the environment, and then when we talk about work, this also needs to be very clear. Another important concept is that the work has to do with the displacement of the point of application of the force, right? In this case, well, the force is applied at the center of the box and the box moves. Okay, so we can say the force is still here. So the point of application of the force and the displacement of the point of application of the force and the displacement of the object is the same. But let's say you had a balloon, I don't know, a balloon, and then you push with both hands. The balloon center of mass is going to stay at the center, but the chances are that the balloon is going to deform a little bit, and as you can see, the point of application will have moved, and there will be work, right? But we will discuss this further later. But even if the balloon did not move, the fact that the boundaries of the balloon move, or the point of where the point of application was, or where, that means there is work. Now consider this: you have the same box as before. You apply a force like this, a force of 1,000 newtons, humongous force, but the block doesn't move, nor the boundary moves. So what's the work? Well, because it's force times displacement times cosine of the angle. Well, first of all, there was no displacement, so there was zero work. Even though we have a humongous force, you need the point of application of the force to show a displacement in order to have work. You can push on the wall all day. If the wall doesn't move, then you technically did not perform any work. How come you become tired then? If you push on the wall all day, you're going to get tired, and the reason is that your muscles, actually the cells in your muscles do move. The fibers in your muscles do move. There is a displacement, and then you are doing work there, and that's why you're getting tired, even though the wall doesn't move at all. Looking at the equation, we can also see how if I had applied a force like this, back in our example with the board and the eraser, if we decompose the forces into vertical and horizontal, notice that this is F sine theta, while the horizontal is F cosine of theta. So in the work equation, you do F delta R cosine of theta. If my displacement is only in this direction, because there is the floor, so you see the F sine of theta is perpendicular to the motion. So there is absolutely no work done by this component. all the work is done by the horizontal component, but that's already baked in the equation. If we consider this free body diagram and we defined the system as the box and the box alone, so we understand then that the force, this force being applied by a hand or a wire, whatever, is external, that the normal is external because is produced by the floor, and the weight is external because it's produced by the earth. Looking at the equation, we can realize that the weight, the work done by the weight is zero because it's perpendicular to the displacement. The work done by the normal is also zero because, again, it's perpendicular. The work done by the vertical component of the force in y, is zero. And the work done by the force in x, well, is F cosine of theta, which is my force in x, right? That's Fx, and times delta r. So that's what it is. Only the horizontal force does work. Only the parallel force to the displacement does work. Let's consider this very interesting scenario. You grab a ball. Come on. Oh, that's not clear enough. We grab a ball and we throw it up. So that happened in the past. Right now, the ball is going up because of whatever you did earlier. So the ball goes from this position to this position. Clearly, there was a displacement. You are not touching the ball anymore, but gravity is still exerting an effect on it. So let's define our system. So the system is the ball, and the ball, of course, moved from here to there. While that happened, gravity was affecting the ball. So if we calculate the total work done, just like before in the earlier thing, if you wanted to calculate the total work on the box, you have to do the work done by the normal plus the work done by gravity plus the work done by the force. And we saw that most of them were zero. So the total work was also this. Well, in this case now, if we want to calculate the total work, we're going to do the work done by all the forces. But there is only one, which is gravity. So we're going to say that the total work is the work done by gravity, which is the force of gravity. Remember, we have to do force, displacement, cosine of theta. So in our drawing, displacement is going up and the force is going down. Notice the two vectors. There is 180 degrees difference between the two vectors. So the force is the weight, mg. The displacement is whatever the displacement it might be. Let's say a distance h from here to here. And then the cosine will be the cosine of 180, which was going to give us -1. So the work done by gravity in this scenario is negative mgh. So two things we extract from here. The work done by a force is not necessarily the work that created the displacement, right? As we can see here. This thing is moving even if the force is acting in the opposite direction. Second, we can have negative work, right? And negative work is a thing, and it happens every time the displacement and the force are anti-parallel. For the units of work are the units of force, newtons, and the units of distance, meter. And a Newton meter we call 1 joule. Finally, work is related to energy. We have not discussed energy yet, but we will see, just like with money, energy will be transferred into or away from the system depending on whether your work is positive, negative, or zero. Like here, the work is zero, perpendicular. Here, the work is negative, and so it is here. Here, the work is positive, parallel, anti-parallel. So in this scenario, you change no energy. Here, the system loses energy, and here the system gains energy. And that's it for today.